Welcome to this session of the Doctoral CMU Portugal Symposium. I'm really glad to be presenting this session. My name is Paulo Marques, and it's a special pleasure for me because I'm actually one of the professors that were involved in the program since the beginning, and I had the first student to actually complete the dual degree in software engineering, so this area is very dear to me, and I'll be hosting this session. We have a number of students that are going to be presenting. Each student will have 10 minutes to do his or her presentation. I will do a small signal at 8 minutes so that you know that you can wrap up, and then you have 5 minutes to answer questions. So welcome and enjoy the session, especially the students. This is all for you. And let's start with Daniel Ramos. He is remote and he's going to present his work. Daniel, can you start?
Hello, is this working? Can you hear me? Hello?
Not?
Is my microphone working?
So I would suggest that we do the following. I would suggest that we go to Maria, who is sitting right next to me, Maria Casimiro, who can present her work, and then we can come back to Daniel.
Okay, so I guess.
Can we put Maria's presentation, please? Oh, Daniel is ready? Okay, Maria.
Okay.
Okay, Maria.
Okay, so welcome everyone, and thank you for being here and for listening. Today I will be talking about our work on how to adapt machine learning components in machine learning based systems. And as you probably know, machine learning is everywhere nowadays, from self-driving cars, fraud detection and medical diagnosis systems, robots, weather forecast. And in this work that we have developed, we consider machine learning based systems to be systems that are composed of supervised machine learning components, non-machine learning components, which all interact between one another. Additionally, these systems typically operate in non-static environments, and they are prone to unpredictable changes. And this may cause the machine learning model to mispredict for some input samples, which in turn also affects the machine learning model's performance and ultimately has an impact on the performance and reliability of the system. As such, machine learning predictions impact overall system utility. And it was based on this that we came up with the vision for self-adaptation to adapt systems to the mispredictions of machine learning models. And particularly in this work, we deal with the problem of what can we actually do to improve the machine learning model. So what adaptation tactics, what actions do we have available? And in order to talk to you about the vision that we had, I'm going to be using a running example from the fraud detection system domain. So just a brief overview of, high-level overview of how these systems typically operate. We have clients that perform transactions, and the transactions are sent to the bank, which then has to either accept or decline the transactions. And in order to do so, the bank relies on a fraud detection system to verify the transaction. And so in this example, the fraud detection system is our machine learning based system. The fraud detection system relies on a machine learning model to issue model scores, which are basically likelihood of the transaction being either legitimate or fraudulent. And this is obviously the machine learning component in our system. And then it also relies on a rule-based model, which is our non-machine learning components, to actually decide whether the transaction is legitimate or fraudulent based on the model score. And so it sends the decision back to the bank. And in this context, we have different types of system utility that we can define and that we give as examples in our work, which are, for instance, the cost of losing clients because of transactions that were incorrectly declined, fairness, or the cost of service level agreement violations. Similarly, also the impact of mispredictions is varied in this context, in the sense that it depends on the clients because they might have different SLAs established with the fraud detection system, and also in time. Because, for instance, during periods such as Black Friday, during which there are a lot more transactions, the cost of declining transactions incorrectly is much higher. And so what we thought was, or we started by thinking about what could actually cause the machine learning model to mispredict. And we thought about dataset shift, which basically happens whenever the distribution of the inputs to the model changes such that it is now substantially different from the samples with which the model was trained. Just to give a practical example, this might happen, for example, if the fraud patterns change and the machine learning model is not trained to recognize those new patterns. Another thing that might happen is when incorrect labels appear in the model's knowledge base. This can happen just because of simple, or just because of human errors, or because of adversaries that intentionally pollute the knowledge base. And in order to be able to deal with these mispredictions, we have compiled a set of adaptation tactics that could be used to improve the models whenever something happens. And for instance, I'll just give one example, and we can think of retrain, which is the simplest example that we have, and could be applied when new fraud patterns emerge, for example. And once we have representative samples, we can retrain the model with those samples such that it is now able to recognize that new pattern. Also, we ground our work in the MAPE-K loop, which is a popular control loop for self-adaptive systems, and is composed of the monitor, analyze, plan, and execute stages. And basically, there are several challenges associated with each of these stages. In particular, monitor, which is responsible for monitoring the performance of the system. There's a challenge, especially in the fraud detection domain, which is that feedback takes quite a long time to arrive, so being able to infer in real time the performance of the model is tricky because we don't have any ground truth against which to compare model predictions. In terms of the analyze stage, we ask ourselves whether the machine learning component is affecting other components in the system, and so the challenge here is to understand how uncertainty propagates throughout the different components. In terms of planning, we need to reason about the costs and benefits of each tactic so that we can understand what tactic is the best one to perform at a given time. However, it's kind of tricky. If you think about the retraining tactic, retraining a model for 10 minutes versus retraining the same model for an hour may yield different benefits. Similarly, if we train the model with a given set of data and then retrain it with a different set of data, the outcome might also be different, so it's hard to predict. And this also impacts the execute stage, which is responsible for deploying the selected tactic in an efficient way. But in order to make it efficient, it also needs to be somewhat predictable. And as I just said, predictability is a challenge here. Finally, the knowledge module may help with all of this because it might keep track of the outcomes of past adaptations and thus help whenever we're reasoning about the costs and benefits. And I apologize for the animations. I don't know why they're just happening now. In terms of the related work, our work is different from what has been done in self-adaptive systems so far, because these systems have relied on machine learning techniques to improve the actual self-adaptation loop. And differently, what we want to achieve here is we want to leverage self-adaptation to improve the actual machine learning in systems. And this has relations to, for instance, the field of lifelong and continual learning, which solves similar problems to those that appear in self-adaptive systems, and also to machine learning, which is where we got some examples of the tactics such as transfer learning and retraining. And so our goal is sort of to leverage the techniques developed by these fields to improve the work that we're doing and create these self-adaptive systems. I just want to leave you here some open challenges that we have also identified. In particular, how can we detect that the machine learning model is underperforming? How can we quantify the impact of these mispredictions, in particular in terms of system utility? And how do we actually choose the tactic to execute? In particular, how can we understand, or how can we compute or know what the costs and benefits of each tactic are? Finally, and just to wrap up, we have seen how machine learning mispredictions affect system utility, for instance, due to dataset shift or incorrect labels, and how we can improve the machine learning model in runtime via adaptation tactics, such as transfer learning, retraining. However, as we have also seen, adaptation might not always be worth it because different tactics have different costs and different benefits. And so it's important to reason about these trade-offs to understand whether the benefits outweigh the costs. Thank you. That's it.
Sorry about this. Questions from the audience? Ines.
Okay, thank you for your presentation. It's quite nice. One question, have you considered any kind of explainability in your machine learning algorithm? So if you want to know why that was the decision, is there any kind of explanation?
No, not yet. Right now we are only working, or we have started working on this reasoning about costs and benefits and analyzing this trade-off, analyzing when it's worth adapting. And I think explainability can sort of be viewed as a pre-adaptation tactic to also understand whether it's worth it or not, but we haven't yet started thinking about that.
I wanted to know, how often do you make this sort of analysis? Is it something like non-line-based learning systems, so considering like data streams, or do you have some specific time points, so after a while you pause and you reevaluate, or how are you?
So the goal of the self-adaptive system is that it's kind of operating on top of the machine learning model, and so it's a continuous loop that is monitoring the system. So it's always looking at, for instance, key performance indicators. We can think about model accuracy, and so it's always looking into that. And based on how those performance indicators change or vary, it might, kind of try to think about whether it would be beneficial to adapt. So whether the utility of the system would improve by doing something.
Any other questions? Okay. Thank you so much.
Thank you.
So we are going to move next to Paulo dos Santos, who is going to present his work. Do we have Paul's presentation? So we are going to follow the program, and Daniel is going to present at the end, so that we keep with the schedule.
Okay.
Paulo.
Okay, thank you. So I'm Paulo. I've just joined the CMU Portugal plan, so I'll be presenting like the ideas and the PhD plan I have for my work, which is type-driven repair for robotic systems. I'm being advised by Alcides Fonseca and Sara Silva from Faculdade de Ciências da Universidade de Lisboa and Christine Perway from CMU. So I'll start by motivating how amazing robotic systems are, okay? So we all know that these have a huge impact in our society. For example, in here we have a large set of robotic systems helping in the production line in a Toyota factory. More recently, we had the Perseverance rover landing on Mars and is currently taking snapshots of Mars and collecting samples. And even more amazingly, right now, okay, let's see if it works. The video, okay, it's not working. So right now you can even have your very own robotic arm to feed your baby. And in the video you'd see a baby getting smacked by the robotic arm. To say what? To say that robotic systems are actually not perfect, okay? Software is not perfect. So in '99 we had the Mars Climate Orbiter crash against Mars, okay? There was a unit conversion bug, which we'll see soon. And most recently, Boeing has been finding bugs in their software. For example, most recently, the warning light of the trim system, which controls like whether the plane, the nose of the plane is going up or down. The warning light had a bug. And we all can see that a bug in these kind of systems can lead to severe losses in terms of monetary, like $200 million with the Mars orbiter, or human lives. So we want to make this software more secure. So what is our plan? So I will start by explaining to you a bit of ROS and the robotic systems composition. So let's say we have this drone, and we want this drone to go from point A to point B, okay? These robotic systems will be approaching, are encoded with the ROS, which is Robot Operating System. ROS allows you to, if you're not an expert, to take different libraries, okay, different components, join them together, and okay, then you have your robot ready to go. On the left side, we have a small diagram of what this drone could be. So we have in orange different nodes that can correspond to components of our robotic system. And these nodes publish to specific topics. For example, the altitude controller publishes information to the motor speed. Or the gazebo publishes information to the IMU, which the altitude controller subscribes. So the truth about this system is that it actually has some bugs, okay? So I wanted to make this interesting. So I simplified this example so that we are short in time, so we can understand. So the first bug is this one. So this specific robotic system, this specific drone, has one component that does not allow the altitude controller to publish negative speeds. If it wanted, for example, to go backwards, it would have to change the direction and go backwards. Nevertheless, the programmer, while programming this controller, let this controller publish a -1, and so we can all know what could happen to the drone if it published this value. The second bug is actually not explicit, and this is one of the, for example, one of the causes with the Mars orbiter. So the altitude controller is publishing the speed of the motor speed in kilometers per hour, while the gazebo, which publishes the IMU, which has, for example, the velocity of the robot, is publishing in miles per hour, okay? And there's actually no conversion between both of these values. So we want to make these verifications. We want to make sure that these conditions and the domain knowledge of robotic systems can be encoded in the target language. So on an overall overview, let's say we take a ROS project, we take a specification, we send it to a static analyzer. We also take annotated standard libraries. We'll see each one of these points. Send everything to the type-driven repair, and by the end of this process, we have our robot working properly, and we ensure the correctness of our robot. Step 1. Okay, so we plan to create a domain-specific language. Okay, so we're going to create a programming language capable of encoding these implicit restrictions that appear in robots. Okay, so instead of having our robot run without these conditions and possibly having it crash, for example, let's provide these conditions to the system, have it verify statically, so we do not need to run the program, and check if the different components of the entire system can hold or not. Then let's annotate the ROS standard libraries. So as I told you, ROS is composed by different modules, different libraries. You can take them all, put them together, and build your robot. So a recent work that was published actually last year saw that actually 82% of ROS applications actually rely on a really small set of packages when comparing with the entire ROS ecosystem. So by annotating these packages, by providing a specification, we can actually improve the correctness of already implemented ROS-based systems and help in the patch generation. And the patch generation. So this is still work for in a few years. But the truth is, if we have these restrictions, we can work as refinement types in our type system. We can use them to automatically generate code that can comply with, that is compilation safe, which is type safe, but also that complies with the restrictions that we had in red. Hopefully by the end of this work, we'll have something that can help developers automatically verify and improve their robotic systems correctness. Thank you.
Questions from the audience? No questions? I have a question. I find it interesting that you are using a dynamic typed language while programming this, and then you are trying to apply static types, and the world seems to be, at least in some domains, moving to dynamic typing. But at the same time, you have languages like Haskell and similar languages that are already very strong in building safe systems, but the world and the engineering people don't seem to be moving in that direction. Do you have a comment? Is this more blue sky type of research or something
okay, so, there was actually a study also made by the same group, which evaluated the problems of, for example, testing robotic systems. And one of the problems that they had was, for example, simulations take too long. And if you want to test a specific robotic system in different spaces, in different situations, okay, it takes too long. So what they usually do is, for example, have it run in the real world, okay, and they see it crash several times. In that study, they said that they wouldn't mind have a form of specification to ensure the correctness of these systems. They interviewed people from companies and also researchers that were, which, for example, some of the packages that are widely used were programmed by them. Okay, so they are really into the ROS ecosystem, and they said that applying this specification, okay, it adds an extra overhead to the development, but it prevents, when they're going to test it in simulation, it prevents them from coming into situations they wouldn't have if they had these analyses and verification previously.
Mm-hmm. Are you making any connection to things like model checking and those types of approaches?
No, at least not yet.
Okay.
So the plan we have different ideas on how to approach this. One of them, for example, is to apply refinement types,
Mm-hmm.
and then build a type checking system to check if everything works properly. Or, for example, apply session types to these robots
Mm-hmm.
to know if what we are publishing and what is receiving on the other side is working properly. So it's still the beginning of the
work in progress.
Okay.
Okay, let's move to the next presentation of Pedro Valdeira, who is remote. Pedro, can you hear us? Are you ready to present?
Yes, hi, can you hear me?
Yes, perfect.
Okay, so let me just connect to the slides app. I wasn't sure if I could do it before the other presentation was over. Okay, so that should be it. No, I cannot see my presentation. I'm assuming you can, right? Hello? Oh,
Perfect.
okay.
Okay, you can start, Pedro.
Okay, so hi everyone. I'm Pedro Valdeira, and I'll be making a presentation about decentralized learning of a mixture of Gaussians from a dataset distributed by features, a topic I worked on with professors Claudio Soares and João Xavier. So the work I'm presenting here today was actually developed just before the start of my PhD, which is being conducted under the advice of Professor Yuji Chu from CMU, as well as Professors João Xavier and Claudio Soares, with whom I continue to work. And in my PhD, I'm still working on optimization algorithms for fully distributed setups, for now by features too, and at the moment still related to the EM, although in a more general setup, not specific to fitting Gaussian mixtures. After a brief outline, this presentation you have here seems to be slightly outdated. Can you this is a Google Slides presentation, if you can just refresh it or something, it should be updated. Because it was a bit too long and I had to shorten it slightly. Can you do that? Okay, perfect. Okay, so yes. Now, if I can just move this. It's not moving the slides now, I think. I'm trying to move to the motivation, which is the next slide, and it's not moving. Okay, perfect. So first of all, why do we care about distributed learning? In the first place, due to an increase in the size of the data to be handled. Computational costs may often require data to be split due to the infeasibility of a single data center training a model on it. But also, data is often already split when you capture it, and we may not want to merge it. This may be due to privacy concerns when different partitions are held by different entities, which do not want to share them, despite benefiting from the collaboration, or due to communication and computational costs, as is often the case, for instance, with wireless sensor networks, where each sensor measures a partition of the dataset. Now, more precisely for this work, why do we care about data distributed by features? This is particularly relevant to ask this question because algorithms for data distributed by features tend to be more challenging to develop, given that the objective function often decouples naturally across data points, but not for the features. However, this is a crucial task to tackle since, for instance, the challenge of massive data sets may not come from the number of examples, but rather of features in setups where D, the number of features each is much greater than the number of data points N. And this would be a computational bottleneck. But also, this is often the case in setups where data is already split, as mentioned earlier, and we don't want to merge it due to, let's say, we have different entities, such as companies who know different features of the same client, or hospitals who have different exams of the same patient, and they would benefit from collaboration, but this data cannot be shared. So this would be the case of privacy constraint. And also the communication costs in wireless sensor networks that aim to learn the behaviors of some random field, for instance. It will also motivate this from the communication bottleneck point of view. We tackle the task of learning Gaussian mixture models in these setups. So the Gaussian mixture model, or GMM, is a distribution resulting from a convex combination of multivariate normal distributions, as you see here in this expression. And they're often used to model subpopulations, as you can see in the images on the left and the figures on the left, and to approximate densities, as you can see on the right. So in the left, the leftmost one would correspond to k-means, and then the second one from the left to the GMM case. And this is just to separate the kind of clustering, because the GMM can perform soft clustering, but it can also perform density estimation, as it performs at the same time when you fit GMM. We usually fit the GMMs by resorting to the expectation maximization, or EM algorithm. So the EM algorithm, suppose we want to perform the common task of finding maximum likelihood estimates of model parameters, written as follows. I'm not seeing the slides moving. I hope you're seeing. Okay, so now it's moving. This MLE, maximum likelihood estimation of the parameters, is often intractable, and DM tackles this issue of not being tractable in models where the model depends on unobserved, so latent variables, which can have a tractable complete data likelihood. We call complete data the one which would include the unobserved latent variables as well. These latent variables Z are often mixture components in the case of GMM, or they can be missing data. And notice that the complete likelihood is such that we get the original one, so the not complete one, when we marginalize out Z. And now a new problem comes up. We do not know Z, and for this reason, if we simply replace P of x given theta by P of x C given theta, we get a problem which is not well posed. It includes random variables. But if we fix theta, we can infer Z, computing the posterior distribution, and based on that, compute the expected value of our objective, P of x Z given theta, and we make it well posed. And we denote this by this expected value by Q, which is a function of theta. And this computation corresponds to the E step from expectation. Similarly, and afterwards we do the update for the parameter estimator theta of R and making it theta of R plus 1. We do this by maximizing Q, and this part is standard maximum likelihood estimation, and we call it the M step for maximization. Notice that each step depends on the result of the other, and hence the M is iterative. We alternate between the E and M steps, and although the likelihood on the actual data is monotonically increasing, this does not guarantee global convergence. And to handle these, we often run the algorithm with multiple initializations and select the best result out of them. Okay, next slide. Let's hope, yeah, it moves. EM for GMM. So for GMMs, the steps are as follows. In the E step, to infer Z, simply apply Bayes rule to each example T and each component K, and gammas are called responsibilities here. Notice that the normalization over the components in the denominator, meaning that it suffices to compute the numerator and then just normalize it. And in the M step, we can simply find the closed form MLE of the resulting Q function with respect to each of the model parameters. Now, before we move to the distributed EM itself, it's important to introduce the consensus algorithm, or distributed averaging. The slide is not changing. Okay, here it is. And let psi n be held by agent n. Consensus delivers to all agents the average of these values by performing an iterative update of each agent's state. And we do this by using a linear combination of the states of the neighbors. You can see, for instance, in the figure, the ones connected to it. Those are the neighbors. And if we have a matrix N with a sparsity pattern that matches matches the underlying network graph, we can ensure local communications. And as long as W suffices a few properties, there's no time to mention them, it allows for convergent exponential convergence. Sorry, I skipped the slide slightly too fast, but yeah, that's actually the point. And in the setup, we'll be dealing with, as you can see here, we have a data set X with data points X1 to XT distributed by features. I hope it's clear from the image. And it's distributed across the N agents linked by a communication network, where XT1 to XTN are the partitions for data points XT in each agent. And we want to design an algorithm allowing us to, wait, this shouldn't be moving. Okay, why is it, okay, I'm not sure. An algorithm that allows us to fit GMM to the full data set X in a decentralized manner. This means we only allow for communications among neighbors, while we impose restriction on the network topology. We don't impose any restriction, sorry, on the network topology. So we can handle general topologies with our algorithm. This is opposed, for instance, to the federated learning setup, where you usually have like a star-shaped topology. And for simplicity, let us consider the case of having a single feature per agent n equal t, although the algorithm generalizes straightforwardly to the general setup. This is just for notation simplicity. Okay. So in the challenges with the distributed EM. Suppose we want to load the GMM on the distributed setup. Sorry?
2 minutes.
2 minutes, okay. We want the memory requirements to be independent from the size of the network and consequently the feature size, which we assume to be equal. Each agent can hold pi and gamma without compromising these, but they only depend on the number of components and t. But while mu can be naturally split according to the features, gamma cannot. So I need to speed up here a bit. But basically, even if you split by feature, you still have like each row, you still have a whole column for each. And if we go back to the previous updates, each agent needs the responsibilities, but in the E step, but these require computing the inverse and the determinant, and in the M step, sigma updates depends on all the features of the data points. So to sum up, the covariants are troublemakers, and they mean that the exact EM cannot be scalable. So our general idea here is to constrain the structure of the covariances. So here now I'll focus on this approximation, and in this presentation we talk about the diagonal approximation, where the memory requirements stop being a problem because each agent holds pi and the responsibilities as mentioned earlier, and also now on top of the mu associated entry also has a sigma entry associated with it. The slides are not moving, but I'll just keep going. And the key idea in the E step is to make the covariance diagonal. So this means that the log responsibility will decouple, given that both the determinant of the diagonal matrix and the inverse have a specific property, which allows them to decouple into a sum, which we can compute using the distributed consensus algorithm. And then for the M step, each agent can simply update locally its covariance matrices, and no communications are required in the M step. So just to sum up, because we're running out of time, ideally this would be the algorithm slide.
Can you conclude?
Yes. And so we just we initialize and iterate within the E step with communications, and the M step with local computations only until convergence is achieved. Okay, that's it. Thank you. I don't know if there's any time for questions, but if there is, I encourage you to ask me about the extension to the block diagonal EM, which is an extension of this work.
We can have a couple of questions. Any questions from the audience? Couple of questions from me. So I'm not sure if I understood everything that you said, but it looks quite impressive. A couple of questions. If I understand correctly, you are assuming that the features follow or the data in the features follow a Gaussian distribution, but if you are not able to look at the data because it's distributed in nature, how are you sure that it actually follows that distribution? Or did I understood it incorrectly?
Okay, so in a small difference is not really a Gaussian, it's a Gaussian mixture, and that actually makes a lot of difference. In like the biggest difference of all is because the Gaussian mixture is known to be a universal approximator of other distributions. So we can there are theoretical proofs that show that you can approximate any given probability density function with a mixture of Gaussians, sufficing that you have enough components, so the K in my presentation. So that makes a lot of difference because in theory, like it depends on the application, but in theory, you can just increase, if you keep increasing the number of components in your mixture, you should be able to approximate to an arbitrary error the divergence of the real PDF from the Gaussian mixture. Was it?
The second question I have is, you have a number of nodes or agents to which you are distributing the data. Do you have any requirements that the amount of data that is in each agent is more or less the same, or how do you deal with the fact that different components can have very different amounts of data? So basically the speed up that you can get will be very constrained.
Okay, so here for notation simplicity, I had the scalar per agent, but this does not need to be the case. We can just have any number of features in each agent. What it means is that if you have more than one, then instead of being exactly diagonal, you start having a block diagonal matrix, where each block is corresponds to the features measured by each node. Right, so you would capture all the correlations within each node. And we actually have an extension of this work to what we call the block diagonal, but it's not just this simple block diagonal where each block corresponds to a node, but it further captures correlations between features measured or observed by different nodes. So even in this setup, you can have as many as you want, and it would become block diagonal, but you can have one with even larger blocks by performing an extension of this work, which I didn't present due to lack of time.
Okay, thank you so much. So we are going now to move to, I'm not sure how to pronounce your name, if you can help me. Abdel. We are going to proceed with your presentation, so if you please. And we need to see the... Okay, perfect. Your floor.
Hello everyone, my name is Abdel. I am a Ph.D. student at the University of Pavilhão. So the title of this presentation is about smart beamforming metasurfaces, the new paradigm for future telecommunications. So this research done under the project funded by Carnegie Mellon Portugal program. So this is the outline of presentation. First I will start with a short introduction. Then I will outline the PhD thesis goal and the challenges associated with this work. Then I will discuss the beamforming metasurfaces, the artificial neural network and the metasurfaces. Then I will present the chessboard mushroom type metasurfaces and the beamforming with the reflected metasurfaces, where I will show you some results. Then I will finish with a conclusion. So metasurfaces are man-made 2D surfaces that have the ability to manipulate and control the electromagnetic waves. These structures are formed by a large number of small, low-cost passive elements. We can control them with an integrated electronics, and they can provide for unique wireless communication capabilities. These figures, for example, if you have a metal plate, if the signal comes with an angle, it will bounce with the same angle, which is determined by Snell's reflection law. A metasurface, for example, the last picture, we divide this structure into a small unit cell, and each of the unit cell has a constant value of the surface impedance. And by controlling that impedance, we can ensure for a signal coming with an angle, it will bounce in another angle. Basically, here we can control the reflection of the signal. So my PhD goal are to develop new architecture for intelligent, reconfigurable multi-beam antennas for future wireless communication. This structure based on smart 2D metasurfaces, powered with AI techniques, and employing programmable metasurfaces layer. We aim also to develop the analytical numerical model of programmable metasurfaces and new AI-based beamforming algorithm. This architecture will be used for real-time dynamic channel propagation estimation and adaptive beamforming. This figure, the first unit cell, show that you can use circuit theory or transmission line theory to develop the analytical model of our structure. So the second picture is just a graphical illustration of neural network with input, hidden, and output layer. The last picture illustrates our main idea here. Our idea here is we are going to split the signal processing between the hardware realized by metasurfaces and the software realized by machine learning technique like neural network, for example. So this PMEs or ERIs, this reconfigurable intelligent surface, they have the ability to manipulate the electromagnetic waves or light. They enable flexible control over the radiation pattern. They can improve the rate and energy efficiency of the wireless channel, and we can use them to control the wireless propagation channel. Also, they can achieve reconfigurable multi-beam antennas. This picture shows that we can steer the beam in different direction, and we can produce different beam. So recently there is a huge body of literature on beamforming metasurfaces. The now operating principles are to control the transmission and reflection phase. By using active tuning of unit cell, we can use the switches, varactor diode, graphene, and so on, and we can control them with an integrated control electronics like FPGA, for example. So the main challenges in realizing metasurfaces are overcoming frequency dispersion and ohmic losses, finite unit cell size and spatial dispersion. There is also difficulties in simultaneous amplitude and phase control, and also the difficulties with multi-beam operation like the level of side lobes. So far, there is two ways that people use AI in some design that involve metasurfaces. The first case is they use AI in the design process in order to design the geometry of the metasurface unit cell. In this case, the INN is trying to relate the electromagnetic characteristic to the design parameter. The second use of AI is namely when AI is used to control the programmable metasurfaces. So currently, we are our current research is focused on reconfigurable reflect array. This structure, as you can see in this picture, this structure is based on an array of small unit cell loaded with varactor, this blue color. So we have developed an analytical model of this structure by using effective medium theory or transmission line theory. And to validate this model, we simulate this unit cell using CST microwave studio or Agilent IDS. And we can see here in this last figure, it showed the reflection phase as a function of frequency for different value of capacitor. For example, I don't know how to point it. So by turning the capacitor from 0 picofarad to 0.1 picofarad, the resonant frequency can be tuned over a range of about 3.4 or 2.4 gigahertz to 6 gigahertz. And we can see that the analytical model, CST and IDS result are in very good agreement. So the first picture showed an array of 3 by 10 unit cell. So using this structure, we can this picture is a 3D of radiation pattern, and the other two pictures are 2D radiation pattern. So the first one is you can see the beam is pointed at 20 degree, and the second one is pointed at 40 degree. So basically here we can steer the beam in different and at the direction we want. So this picture showed an array of reflectors with the controllable phases, and we have a source antenna. So by applying the Fourier transform, we can relate the far field pattern to the antenna aperture. So here we can control only the phase of the phase of the reflection field. So this formula is a function of u and v. It's give us the expression of the field, the electric field, far field pattern realized by this structure, by this metasurfaces. So when we get the reflection field phase, we optimize the reflection phase distribution using some algorithm. So here we want to optimize the radiation pattern by decreasing the side lobe level of by decreasing the side lobe levels. So by using this some optimization algorithm. So here we divide this radiation pattern into two main area. The main beam area. This is when I have this ellipse red color, and the other side lobes area. So here we basically want to optimize the structure. We keep the main beam area, but we want to decrease the side lobe of the radiation pattern. So what has been done so far is this proposal has been defended. The analytical model of the structure has been developed, and the unit cell structure of this PMS with memory has been proposed. The numerical model of the proposed PMS structure has been realized in CST and IDS, and a set of simulation has been performed. Also, the beamforming techniques have been investigated, and now we are in the final stage to produce the first prototype. Thank you.
Thank you. Questions from the audience?
I didn't understand. Maybe you can explain again. Sorry. What do you actually use AI for?
So we can use UI in two things. We can use AI just to control this structure. For example, we have some diode here, and we want to apply some voltage. So we can use AI just to control this structure. For example, if you want to steer the beam in this direction, we want to apply some specific voltage here. If you want here, we are so. And the other use of AI is now we are actually we start working on that. We want to use the analytical the theoretical stuff to produce a set of data of this electric field, and we want to use this data to train the artificial neural network.
Okay. Okay. Thank you.
Okay, thank you. We are going now to move to Daniel Ramos, who is remote. And Daniel, can you hear us? Daniel?
Hello? Hello? Can you hear me?
Hi, Daniel. Yes, finally.
Perfect.
Session. So we cannot see you. Can you actually? Hi, Daniel. It's nice to see
Hello.
your face. Yes. So the floor is yours. You can start. 10 minutes, please.
Mm-hmm. Yeah, I'm just waiting for my slides. I can't see them yet, but I can start anyway. So, while the slides are put on the board. So I am Daniel. I am a software engineering PhD student at ISR, also at Technicum. And today I'm going to tell you about work that I did in the last year. It's about synthesis for API refactoring. Let me see if I get this to work. Perfect. Okay, so I have here one small motivation example to help you understand what I did. And so let's start by supposing we have Alex. And Alex is a data scientist that wants to create a machine learning model to make a speech recognition system. And so the most common way to do this nowadays is simply to use some sort of machine learning framework like TensorFlow. And so Alex starts writing some code using TensorFlow, and they even get far enough as to write some test cases. But then let's suppose that Alex realizes that TensorFlow is not really a great fit for this problem for some reason. And they want to use an alternative framework like PyTorch. So PyTorch is essentially an alternative / competing framework for deep learning. And so the question that I want to ask here is, if Alex wants to switch the dependency of TensorFlow from his code to PyTorch, do they have to start over from scratch? So that's the question that I aim to solve. And the slides are not working. Okay, great. And so this problem I just introduced is an API migration problem / refactoring, and it applies to many domains, particularly data science. The reason that I picked data science here is because data science is constantly evolving. It's a new field, and so new libraries start emerging, some start being supported, and so it's a particularly good example for this task. And to show you something concrete, for instance, PyTorch today is one of the most ubiquitous deep learning frameworks, as hasn't always been the case. In the past, TensorFlow used to be way more dominant than PyTorch, and that's slowly changing. And so what I did, or what we worked on, was a method called SOAR, and SOAR stands for a synthesis approach for API refactoring. And it's essentially a tool that you can use to migrate dependencies of your code. So we say it's an end-to-end technique because it does everything from end to end. And so to one concrete example, picking up the TensorFlow in the PyTorch case. So let's say we have this source code on the left that depends on TensorFlow. And what SOAR does is it places all calls, all dependencies to TensorFlow with PyTorch equivalents. And so how can we do this? So SOAR is based upon 3 key observations. The first is that data science APIs are generally well documented. And to show you one concrete example, this is the TensorFlow Dense API, one of the APIs from the example earlier. And this is the documentation page. You can see it has a small description here. And if you scroll down, there's also a more detailed description with more information regarding the behavior of the API. And if you scroll down, we also have a list of parameters. And this all happens in PyTorch. So it also has the same structure. The documentation page for the API is similar. It also has a small description, a list of parameters, and if we scroll down, there's also more details regarding the behavior of that API. And so what we do in SOAR is we use the documentation of the libraries to train a machine learning model to map source APIs to target APIs. So in this case, for TensorFlow in PyTorch, let's say we have on the left, this table here shows the source APIs that we want to migrate. And we have the APIs that SOAR computes using the model. And so using this, what we can do is we can go into the original source and replace the dependencies in TensorFlow with PyTorch equivalents. You can see here I'm replacing dense with linear. But there is one problem with this. And that problem is that the API mappings don't tell us anything about the arguments of the new APIs that we are replacing the old ones with. And so in the case of dense and of the APIs TensorFlow dense and torch.linear, you see there's a mismatch between the number of arguments of the APIs themselves. So TensorFlow dense takes just 1 input and torch linear takes 2. So we have to compute those 2 arguments. And so this leads us to our second key observation, and that's the fact that this problem of computing arguments is a great fit for program synthesis. So that's where program synthesis comes in. And so our idea with SOAR is we scrap the documentation pages and we collect information regarding the argument types and the constraints of the arguments of every API in the target library, in this case PyTorch. And we start enumerating possible values for the arguments of the APIs that we are migrating. So it would look something like this. For instance, this API here that's highlighted, it's one of the APIs we have to fill in the arguments in, and so it takes two inputs, x1 and x2, and we just start enumerating possible values for the APIs until we find one that passes the test cases. Okay, so the key takeaway here from this second step is that the SOAR also uses the documentation to guide the synthesis process by collecting information from the documentation page. That's very structured. And then our third key observation, final, is that well-documented APIs generally also have informative error messages. So what we do in SOAR is so what happens when we are trying to enumerate possible values for the arguments of the API? It's often the case that we generate stories that do not make sense in the context of that specific API. So here, for instance, if you try to evaluate this torch.nn.linear with -1 as an argument, and if you try to run that on the Python interpreter, the interpreter is going to complain, and it's going to output this this error message here, and it says that trying to create a tensor with a negative dimension is not allowed. So what we do in SOAR is we parse the error message again with a simplistic machine learning model to create constraints on the arguments of that specific API, and that allows us to narrow the search space of possible values that we have to consider when synthesizing the arguments. Okay, just a second. Right. Okay, so we evaluated SOAR to show you that it works. We evaluated SOAR in two domains. The first task, we had 20 tasks from TensorFlow to PyTorch and 20 tasks from dplyr to pandas. So SOAR is language agnostic. It works across languages. And for this talk specifically, I'm just going to tell you about the results that we got from the TensorFlow to PyTorch tasks, and those correspond to migrating simple and not necessarily simple, some machine learning models, neural network models, 3 and up to 44 layers, and we include some particularly well-known networks like VGGs, well, AlexNet, LaNet. We also have autoencoders among others. And so to show you the impact of each idea that I discussed throughout the talk, this bar chart here, the percentage of benchmarks from the 20 that we solve for the TensorFlow to PyTorch task, we have a timeout of an hour. So what we do is we try to migrate each program within an hour. And so the y-axis is the number of benchmarks we solve, and the x-axis is the of SOAR that we turned off for each evaluation. And so in this first bar here, that's actually a 0, so it doesn't show up. We just turned off the we turned off the API mappings. So that's the idea I discussed, creating API mappings between source and target. If we disable that and we use site, and if we enumerate random APIs, we cannot solve any of the benchmarks. And this makes sense because TensorFlow and PyTorch had both huge libraries with over 1,000 APIs. And if we move to the right, so with the synthesis without documentation, that means that we just, for that specific case, we just turned off the documentation information for the synthesis, for the enumeration of arguments. And in that case, 25% of the benchmarks that in this specific scenario, what we did was we just and the third bar shows the performance of SOAR without the error message understanding model. And we already have a great performance, and the fourth bar shows the full approach, the 80% of the benchmarks that we can solve. Okay, so here I have one concrete migration example. So this is on the left. We have.
Okay, you don't. Can you conclude, please?
Sure. So this is just a migration example. I can show it later. I can show the links to the repository. But essentially, I wanted to wrap up by saying that this work was published at ICSI this year. This was a very big project with a lot of people. And I have here a QR code if you're interested in learning more about SOAR. And since I don't have time, that's it.
Okay, thank you. Questions from the audience?
So Daniel, I'm not sure if you can hear me. I'll try to speak loud. Thanks for the presentation. It was really interesting. My question is, I'm guessing it has to be crucial for you to be able to, say, understand in an automated way and in a precise way exactly what documentation stands for and also the error messages stand for. So I guess you need to have a systematic way of understanding documentation. Can you say something about how you do this?
Students involved in the project, but I can tell you that what we do is we use. So the thing is, TensorFlow and PyTorch have very structured documentation pages. So they always follow the same pattern. They're very well organized. And so what we do is we got all the documentation pages from TensorFlow and PyTorch from the web. And then we used I think we are using the glove model to compute embeddings. And essentially for each API, we create I don't know the machine learning keyword here, but we create like an embedding a representation of that API in a vector, right? And that's obtained from the words that are there in the description of the API, and then we try to each API against each API in the source library against the each API in the target library. So essentially, you have a vectorized representation of all APIs that contain some sort of meaning, and we just try to compute, check for the one that matches best for each pair. I'm not sure if that answers your question. I could try to elaborate on this, but this is not my.
Any other question?
I have one. So, Daniel, I was wondering, do you always have a mapping between the TensorFlow, for example, a function in TensorFlow to PyTorch?
Yes, that's something interesting that I want in the migration example, but I didn't have time. So sometimes we cannot really. I'm muting myself. Can you mute me, please? Can you please mute? Otherwise, I can't speak. Thank you. So I was saying that sometimes it's not possible to find a mapping, one-to-one mapping. So we the behavior in TensorFlow. So to model the behavior of TensorFlow in PyTorch, we might need to use a set of APIs instead of just one. I think that's what you were asking. And so we do support too many mappings as well in SOAR. And so to model to get the same behavior in PyTorch that we had in TensorFlow, we used multiplies in PyTorch. And that worked for our set of benchmarks.
Okay. Ask another question.
Go ahead. Last one.
It's the last one. Okay. How do you guarantee the semantic equivalence between the original code and the synthesized code?
Yeah, that question makes a lot of sense. We have test cases. So essentially, when we ask the user when the user wants to migrate code using SOAR, we ask for test cases. And so and for the specific two libraries, test cases are just some tensors. So it's essentially a matrix, right? And so what we do is we simply run the neural network through that tensor and see if the outputs of both programs match. We also set the specific values for the network. So the weights, we set the same weights and the same parameters for both networks across the libraries, and that's how it works.
Okay. Thank you so much. So we are going to do a short break. I thank all the students that have presented. It was quite interesting. And we'll get here at 4 p.m. I think. Thank you.
Okay, so good afternoon. I'm Lia Patrícia, and I'm coming from the Faculty of Engineering of the University of Porto, and I'm very pleased to be here for the session on engineering and public policy. And today we will have first Afonso Amaral and then Ji-Hoon Shin, who will present their work. Welcome Afonso and welcome Ji-Hoon. So today, because we had Rashmi, who could not attend and could not participate, we will have a bit more time. So instead of the 10 minutes, if you want to take 5 more minutes, it's okay, so we have time. And so I think that we can start with Afonso. Thank you, and let's listen to you. Okay, and welcome.
Thank you very much. I hope everyone is seeing my slides.
Not yet.
Let's wait for the organization. So, maybe you can mute yourself. Okay, I think you are now, correct? Okay, then let's start. My name is Afonso Amaral. Thank you so much for giving me the opportunity to present my research. While I have a background of mechanical engineering, I'm doing engineering and public policy Ph.D. advised by Erica Fuchs, Joanna Mendonça, and Granger Morgan. Today we're looking into the relevance of national core competencies in times of crisis. We're specifically going to look into the regulation of mechanical ventilators in Portugal and Spain. So the ventilators are seen as the last line of defense against COVID. Essentially, 1 in every 10 people that enter the hospitals with COVID can get intubated. And so fulfilling the worldwide demand of mechanical ventilators can actually save lives. But what are mechanical ventilators? Essentially, they are those very complex machines that pump air into someone's lungs. And the problem is that due to the nature of this coronavirus, there was national shortages throughout the world. So just before we start, my research question is, how do differences in internal competencies explain regulatory and policy responses and the emergence of new entrants in Portugal and Spain? Here, I have done 55 semi-structured interviews across Portugal and Spain in the relevant stakeholders. We have new entrants in both countries. We have suppliers and manufacturers, as well as the associations of such firms and the competent authorities of both countries. We have also complemented this with interviewing high-level people in the European Commission. So essentially, the idea is to look into these mechanical ventilators, which represent knowledge-intensive safety-critical products, which are life-supporting products, which know a lot of tacit knowledge embedded into them. And we're looking into the actions that national governments can take to address market entry barriers. So they are trying to see, how they have helped these manufacturers trying to overcome the challenges in this market. It's a very risky product, highly regulated, is very sophisticated, and it's dependent on its supply chain. So if we look into just a little bit before, if we're going to look into the numbers, in 2019, before Corona actually spiked, there was 77,000 units worldwide. When Corona happened, United States alone wanted to acquire almost 3 times more. And so it is fair to ask, how can the market keep up with this increase in demand? Which market is this? Essentially is dominated by a few big players around the globe. North America, Europe, and Asia is technologically advanced products and is extremely regulated. We have seen an increase in both imports and exports in European countries, which suggests that, but the imports are bigger than the exports. And this suggests a tendency for national protectionism. And it might be, every country might be dependent on their internal domestic productions. So just before that, let me summarize to you very simply how the process starts. If I want to introduce a product in the market, how does it work? First, I have to get these preclinical trials approved. Then I have to test it on the people. Both of these steps are under the competent authority. Then I have the CE marking, which a lot of people might have heard, which is the European certification made by these independent notified bodies. Once the product is approved, you just enter the market you want to enter, and you are on this post-marital surveillance. The first 3 steps are made once per product, and we're going to focus on those, and the last 2 are made once per country. Before I show you my findings, I want to clarify that a derogation measure is a special permission to change these rules. If it's necessary for a country to do so, they will do so. So, findings that we have found. The big puzzle is, with the shortage of ventilators, both Portugal and Spain have created extraordinary approvals. While Spain only was active for 3 months, it approved 12 products. And while Portugal was, for at least a year, it only approved 1 product. Out of these 12 products, 3 of them went to the CE marking, which means European certification, and 9 were taken out of the hospitals, so that in case any shortage. The one approved in Portugal was submitted in May and only approved actually in December. It is a little bit more complicated than this, because there was another manufacturer in Portugal that just decided to go strictly to the European regulation instead of using this supposedly easier extraordinary approval. And there was even another one that didn't do any of this and just placed the products in the hospitals, but they were not used eventually. So let's compare both and into 5 different dimensions. If we go talk with the people and we receive different perspectives, and so it is no one ever made a decision on regulating a ventilator. No one wants to open a precedent. When we look into both derogation measures, which are these approvals, these extraordinary approvals, into 5 different dimensions, we can see that while Spain did a clinical investigation, which is normal, Portugal did an exceptional authorization nationwide. So Spain only did it in 3 months and Portugal did it for more than a year. However, Spain was more successful, approving 12 and Portugal only 1. This is also due to the fact that Spain did something simpler than Portugal, because Portugal just copied the regulation that was currently being used. And so Portugal needed an external task force because there were no notified bodies in the country. But we'll get back to it in a second. Just before we go to those 3 main steps that we talked about before, the Spanish competent authorities stayed within their competency, and the Portuguese did this nationwide approval requiring external knowledge, so they had to require a task force for that. And while we already saw that Spain only approved devices for 3 months and Portugal for more than a year, the truth is that they are 1 month apart. And if we look at that month and we compare it with the number of cases, Spain implemented this derogation measure where the cases were spiking up, while Portugal took almost a month to do so, showing the difference in reactiveness of competent authorities. Well, Spain seems indeed to be better prepared to respond to a potential shortage of these types of medical devices because they do have a notified body, a public one, and they also have mechanical ventilator manufacturers, and Portugal only has medical device manufacturers, but not specifically ventilators. And Spain has 2, who managed to ramp up the production of 100 units per year to about 5,000 units in 9 weeks. So Portugal, it might be more dependent from new initiatives than Spain, although it only approved 1. I love this quote from an interview I did, which is the Director of Innovation and Product Development from the industrial partner that allowed this to happen, the 5,000 units in 9 weeks. She says that Spain was successful because of 3 reasons. It had technology and the knowledge to develop ventilators. It had our firm, so their firm, which managed to ramp up the existing production, and had a government who helped in the procurement process and invested in national industry when it was necessary. So what can we conclude from here? First, once there's a product shortage, either a country has manufacturing or it does not have manufacturing. If it has manufacturing, then it's fine. Or if there is international aid, it's also fine. But if it does not have manufacturing, if it's not enough, it will rely on new entrants. New entrants are essentially firms from different markets. They don't necessarily know how that market is because they are not there by definition. So it is necessary to cope with the dynamic external environment and adjust the regulations we have. So we need these dynamic regulatory capabilities to facilitate these new entrants. The problem is that without manufacturing, there is no dynamic regulatory capabilities, and this is what we found. we've seen that a lot of countries across the globe have found themselves in this loop. Now, if you look into the upper part of the slide, if there is manufacturing, then there are also dynamic regulatory capabilities which can facilitate new entrants to enter the market. So if we cross the product safety relevance with the types of products, and if you look into the shortage of these products, if product is not critical, then we can rely on international trade because we go to the market and whoever is selling it will sell it to us. However, if it is safety critical and there are times of shortages, then there might be an issue. Well, if the product is simple, it might not be essential to have this dynamic regulatory capabilities and adjust the standards and the whole thing because it's simple to produce. But if it's complex, then there might be a problem. So let's focus on safety critical products. So if we map that against the existence or non-existence of domestic manufacturing in a country, it means that if there is existence, we already know that there is also these dynamic regulatory capabilities and they exist to help the manufacturing ramping up, or if it's not enough, to help these new entrants to enter the market. But if they don't exist, then they just don't exist. And you cannot really help anyone because you can just rely on the standards that you already have. So if the products are complex, they might be relevant to help the producers to ramp up, but if it's simple, it's not necessarily essential. However, if we don't have these regulatory capabilities and we have a shortage of complex product, it is essential to have those. And this is a problem. And again, it's a loop that a lot of countries found themselves in. So to finalize, our empirical research suggests that the notions of core competencies and dynamic capabilities can be used in context of nations and our powerful tools to actually predict how different countries will respond, who will thrive and who will struggle. The existence of manufacturing rather than its size of capacity is what determines if a country has dynamic regulatory capabilities. And this is especially relevant for smaller countries because it's not the size of the capacity, but the existence of it. And finalizing, while some minimum national internal competencies might not be paramount during normal times, they are pivotal in times of crisis to protect national interests. And this is relevant for both European Union because we are sovereign nations, as well as the United States. And so the implication essential is, with the framework we propose, we advocate for countries that should systematically review their potential vulnerabilities, making sure they sustain minimum competencies and capabilities. Thank you.
May I? Okay, thank you so much, Afonso, for the interesting presentation. I would ask if there is any question from the audience. Otherwise, I may ask a few questions. So one of the things that I found very interesting in your work is that you bring in the notion and the concept of dynamic capabilities, this sensing, seizing, and reconfiguring into regulatory dynamic capabilities, and I found that very interesting. But on the other hand, I had that question: what do you mean by dynamic regulatory capabilities, and to what extent do they differ from what we know as the standard dynamic capabilities? Can you?
So that is a question we had to address once developing this research. And indeed, you're right. So the regulatory term that we introduce here is just to specify which type of dynamic capability we're talking about. Because both, if you talk about resource-based views, so the resources or the core competencies or the dynamic capabilities, there are several of them. And we are trying to focus specifically on the connection between the competency of manufacturing within a country and the dynamic capability that country has to regulate if there is, a crisis. For example, we had to adjust the standards. We have to talk with the manufacturers and see if there's anything we can do to help, for example. And so coping with that dynamic environment and having that dynamic regulatory capability, we found that it actually exists because there is core competencies such as manufacturing in the country. So to answer in 2 words your question, we just tried to narrow the scope down of dynamic capabilities.
Okay. may I then comment and add another question, which is, so from what you are saying now and what I heard and saw from your abstract, of course, is very short. So it seems that somehow you on the one hand, you are extending the notion of dynamic capabilities to the national level and thinking about that it can also be an important capability, an important dynamic capability, not only to seizing and reconfiguring and innovating in terms of new products and services for the company and the organization, but also in terms of the regulation. So regulation as somehow an innovation, so you can innovate in terms of regulation, and so the dynamic capabilities to innovate as a regulation, or in terms of the regulation to respond to the market changing needs. I think it's an interesting point. The other question that I had was, so then it seemed to me that from your results you are relating somehow that you have like dynamic capabilities of the organizations or of the companies in the country in a specific sector, in this case the ability and the manufacturing of ventilators. And then you have at the higher level the dynamic capabilities, and it seemed to be that from your results you are connecting the two. So you need to have both the dynamic capabilities, or at least the minimum level of dynamic capabilities at the industry level, so that you can leverage upon that with the regulatory dynamic capabilities. Is that so? What do you think about that?
Yes, so that's an excellent comment, because the research on national competencies and dynamic capabilities is very limited. And so that is one of our core contributions, is exactly that. We are trying to make it obvious, or we have found with our research, that the existence of firms in a country actually it translates to the same to competencies and capabilities of nations. And so if we have several manufacturing sectors in a country, we can talk about the core competencies of each a company and how they innovate and whatsoever, which resource they have. What we're trying to say here is that is correct. However, the location of the firms, the locus of production, will also give the sovereign nation that is hosting that competencies and capabilities. And this was very clear if we look, for example, to the US. Once you have companies such as Philips, which is from the Netherlands, it's producing in the US, and then President Trump at the time enacted the Defensive Production Act, not allowing the company to supply their own country. And so that gave US leverage, and this competency of producing these devices they actually needed. While Philips is a firm that is from the Netherlands, but they were not necessarily able to supply that same country. So again, in one sentence, one of our main contributions is not only say that yes, you can apply these concepts in nationwide, but the firms that you're hosting in a country will also translate to the competencies and the capabilities that a country has.
Okay. Thank you so much. And I think we need to move to Ji-hoon. Thank you. And okay, Ji-hoon, the floor is yours.
Okay, thank you. First, I'm really happy to deliver the presentation today. I'm Ji-hoon Shin, a PhD candidate, and now I'm staying in Pittsburgh, so I have to do the presentation online. I have been supervised by Ana Barros and Miguel Amaral from Portugal side, and then Granger Morgan and Percy Vaishnav are co-advisors for my research. Today I'm going to talk about the presentation titled with How Does General and Specific Capital Drive Technology Development in Firms? So technology is very important. Everyone knows that. So technology is considered as a critical factor to improve firm performance and accelerate industrial development. So that's why all the firms and the governments are trying to develop technologies, and they are trying really hard to increase technological capabilities within an organization or a nation. But much literature has focused on many dimensions of the factors influencing on technological development. Some of them are focusing on research and development, and some of them are focusing on foreign direct investment. And much of literature also has focused on the role that human capital plays in explaining technological development. So here, human capital means the laborers or workforces of the firms. But there is limited consensus about which dimensions of human capital influence the technological improvement of firms, meaning that someone think that education or work experience are very, very important, but someone also think that age or IT technologies are very, IT abilities are very important for improvement of firms. There are two possible reasons to explain this limited consensus. The first one is about imperfect measures for technological development. So far, the previous studies adopted indirect measures like firm survival, firm sales, number of employees, number of patents, and R&D intensity. And all of them are indirect, so sometimes they failed to directly measure the technological development of the firm. And most of the previous studies also rely on easily biased measures, such as self-evaluation. In that case, they do surveys towards the workforce of the firm, and then workforces or laborers, they evaluate by themselves. And then, of course, naturally, it can be easily biased. So as a result, cause some distorted results in the previous study. The second reason is the imperfect data, meaning studies are focusing on very specific types of firms or technology-based firms or startups are highlighted so far because they are the foundation of the technology generation. And then high-tech industries like the semiconductor industry or aerospace engineering have been highlighted or focused by researchers because that is easy or dominant fields related to technology development. So here, this study contributes theoretically in terms of the measurement. We developed and applied a new and original measure of technological development. Each firm has an industry classification code. We categorize the codes to four categorization, from low tech to high tech. So there are four categories like low, medium high, and high technology intensity. It is following the standards of Eurostat and OECD. We track firms' transition among those four technological intensity levels. So let me give you some example. So here is company A. They start their business from metal parts manufacturing, and then they can move to the machinery industry, and then they pass through automotive industry, and then finally they do aircraft-related business. So here we can find that their technological intensity starts from the low level, and then they move to the higher level. So meaning that this company A actually achieved technological development. So this kind of transition, and we can track this transition among those technological intensity levels, and then we can assess their technological development or achievement through the years. After measuring the technological development, we can directly link human capital and technological development, and we empirically test hypotheses with the data covering nearly all types of firms and industries. Here, we developed 5 hypotheses. The first one is about general human capital, meaning that, general human capital means that the overall ability of the laborers of the firms. The first hypothesis is education level is positively associated with technology development. And then second one is about work experience. From here, we developed hypothesis about specific human capital, meaning this is totally related to technological knowledge. So here, STEM education and the same industry work experience are positively associated with technology development. The last one is about the combination of STEM education and the same industry work experience. So if the worker has 2 backgrounds from STEM education and the same industry work experience, it would be positively related with technology development. We test this hypothesis with the data from the Portuguese government called Quadros de Pessoa. It is the mandatory survey by the Portuguese Ministry of Social Security and Labor. It nearly covers all the companies and their employees in Portugal. Of course, it also covers nearly all industries in Portugal. It is very unique data that we can match employer-employee. And we adapt the data from 2009 to 2015. We also applied logistic regression model for this hypothesis. And we adapt control variables like foreign capital, initial capital, private capital, firm sales, and number of workers, because all those are considered as a critical factor for technological development. Here you can see the results. Among general human capital hypothesis, education level is statistically significant. And among specific human capital variables, work experience, the same industry work experience and STEM education and the same industry work experience are positively associated with technology development. However, general work experience and STEM education are not associated with technology development. So you can compare those 2 results among all the general human capital and specific human capital variables. This gives some theoretical and practical implications for us. So for managers and policymakers in the government should think about the equilibrium among 3 major factors: the general education level, STEM education, and the same industry work experience for technology development. All these 3 are equally important, and it is the critical factor reflecting our result. So general education level might shape more supportive work experience because more educated workforce can communicate more efficiently and effectively, and they know how to lead the team, they know how to set up the goal. So they may have better communication skills and leadership skills, so it would be much more supportive for technological development. STEM education is not valid, but it can be valid if workers at appropriate level of industry and firm-specific knowledge. So always STEM education is to be complemented by the same industry work experience. So meaning that it is very critical to hire workers who have both, and otherwise it is very necessary to conduct on-the-job training, or it is very important to give very realistic problem-solving skills or problem-solving tasks to articulate their skills and to link their STEM knowledge with the same problem-solving. And it is also very necessary to collaborate with a university. For example, the governments can intervene the relationship between the universities and the firms, and then they do co-work to improve their educational syllabus or curriculum, and then they can make a linkage between their STEM education and the real problems. So these kind of implications are very important to increase the possibility to generate new technologies in the firms and even at the nation level. Thank you for listening to the presentation, and please feel free to ask any question. Muito obrigado. Thank you.
Thank you, Ji-hoon. Thank you very much. Questions from the audience? Okay, if we don't have, I have one, and maybe more, but at least one, because I know that we need to keep up with time. So Ji-hoon, thank you very much. That is a really interesting study and a very interesting set of data. So how you build the data set, I think it's also interesting. I was really puzzled by the fact that, and so in your conclusion, you took some conclusions about and implications on the combination of STEM education and work experience, specific work experience, but it puzzled me that STEM education per se, so education in science, technology, engineering, and management, wouldn't have a significant impact on the technology development as an outcome variable. Do you have any explanation for that to happen? Have you thought
I think the other kind of education could be included in the general education. So, of course, all the knowledge about finance, marketing, and some other engineering stuff can be linked to very specific technology development. But I don't think it does not have a direct impact on very specific technology development. As I mentioned and as I explained before, that would have indirect impact, like giving more supportive environment, and then they may generate better environment to invest money or invest more resources on technology development. For example, financing is one of the critical skills, even in terms of technology development. But it is not just because they have direct impact on technology development. If top management team or entrepreneurs have financing experience or finance-related knowledge, they can give better signal to investors, and then they know how to loan from the bank, and then it means that they can invest more resources or finance stuff to research and development that may generate or increase the speed of technological development. So like that, I think that could be included in overall education level, but it does not have very direct impact on technological development.
Ji-hoon, thank you so much. I don't know if there is any other question, or otherwise we need to finish. Okay, thank you so much. Okay, I think we close this section.
Hi, can I start? Good afternoon. Welcome to the session on electrical and computer engineering as applied to healthcare. We're going to have 4 presentations today. We have 1 speaker remotely, 3 that are here with me. And we will start with Joana Rocha. She's doing a thesis on transparent AI at Inesc Tech. Welcome, Joana. You have 10 minutes to present your work and then 5 minutes for questions. You may start whenever you're ready. No sound. We cannot hear you. Hope she's there, but we cannot hear her voice. Right. Not yet.
No.
We still can't hear you.
Can you hold a moment, please?
Maybe we can go ahead with one of the people here. Okay, Joana, you'll be next, hopefully. So let's go to Sofia.
Okay. My work is also Joana's work, actually.
Okay.
So
perfect. So it doesn't really matter which order we go in. So I think Sofia, again, you have 10 minutes for presentation, 5 for questions.
Okay.
And hopefully you can start as soon as you have your slides. No image, no slides.
They're here.
Okay, perfect. Okay.
Okay, so hi, my name is Sofia. I'm involved at a CMU research project called Transparent Artificial Medical Intelligence. I'm going to present on the segmentation of COVID-19 lesions in CT images. This work was developed by me and my colleague Joana Rocha, together with Professors Aurélio Campilho and Ana Maria Mendonça. It was actually presented at a conference a couple months ago. So unfortunately, the new coronavirus does not need a large introduction. It has brought devastating consequences worldwide on people's health, on the global economy, and in society in general. We know that the manifestation of the virus in the lungs is among the first signs of infection, and due to the urgency of the matter, a large amount of research was very quickly published. What happened is that many of these research papers are poorly reported and lack proper peer reviewing due to the urgency of the matter. Being able to automate the segmentation of the lesions caused by COVID-19 can be of great value, especially for patient diagnosis and prognosis, and also for hospital management. With this in mind, the goal of this work was to develop a segmentation model for COVID-19 lesions in CT images. Regarding the data set we used, it was made available at the COVID-19 20 Lung CT Lesion Segmentation Challenge. The annotations were already provided by the challenge. They were made automatically and revised by radiologists. The data consisted of CTs of 199 patients with positive PCRs for SARS-CoV-2. We started by pre-processing the data. So first, we transformed the CT volumes into 2D slices. We discarded the slices in which there were no pixels containing lesions. We truncated the intensities and normalized the intensities of the images also. After this initial pre-processing, we wanted to take some additional measures in order to make sure that the input to the model was as good as possible. So we cropped a region of interest around the lungs, because obviously there are no lesions outside of the lungs. And we enhanced the contrast of the images. After all these steps, we ended up with approximately 5,000 observations, and each observation is a pair of one CT slice and one lesion mask. The main challenges associated with this work were two, essentially. So the first is the huge class imbalance, because most of the pixels belong to the background class. So most of the pixels do not represent lesions. Actually, more than 99% of the pixels in each image were backgrounds. So this was one of the main challenges. The second one is the high lesion variability in terms of size, shape, and quantity. This was actually transforming the data from 3D to 2D might have made this worse, because we are slicing the volume, which increases the variability in each slice regarding the appearance of the lesions. Regarding the methodology, we used UNet with a ResNet 34 as an encoder. This slide is actually, it's my fault, it was not updated. So we did cross-validation in the training and validation test sets, and we used an external test set. But the training and validation percentages that are on the slide, they were rotated 5-fold, so we performed cross-validation. In order to make sure that we were taking the extreme class imbalance into account, we used the dice loss, which is an objective function that takes into account the overlap between the prediction P and the ground truth pixels, the ground truth of the mask G. Regarding our results, we decided to compare them against the leaderboard of the challenge where we took the data from. The results are quite comparable, quite similar, although they cannot be 100% comparable for mainly 3 reasons. First, because the winning solution used a 3-dimensional approach, and we decided to decompose each volume into 2D slices. Second, we used less training data because we did not have access to a specific portion of the set. And finally, the validation, well, this third point is actually a consequence of the second, so we ended up using different validation and test sets when compared to those used in the challenge. But still, the results are quite similar. This illustrates some of our results. We start with some good examples. So the green pixels represent the true positive pixels, while the yellow pixels are false positives and the red pixels are false negatives. So we can see that overall, the network is able to correctly segment the lesions. It does not seem to have a problem with slices that contain more than one lesion. Oh, did I? Oh, okay. More than one lesion, and also it's fine with bigger lesions, smaller lesions, so it's, at least in these 4 examples, the variability of the lesions does not seem to be a problem. However, there are not as good examples, so you can see here that these examples are less satisfactory, I would say, mostly in terms of quantity. So sometimes there are some lesions that are not detected at all, and some other times the extent of the lesion is not very well assessed, as you can see in the right image. This is to demonstrate that turning the 3D result into a 2D set of slices did not affect what we call the patient-wise coherence. So when we transformed the data from a volume to several 2D slices, we were afraid that the consecutive slices would not have similar results, and that would of course be bad, because that would indicate that the model was not working properly. So we can see here that consecutive slices, obviously from the same patient, have very similar segmentation results. So to conclude, the network is in fact able to correctly segment the abnormalities, even with the very diverse size and shape. It occasionally miscalculates their extent or misses smaller lesions. There are some major setbacks, which I would say are very typical from the medical domain, namely the complexity of the anatomic structures, the noisy, blurred and or low contrast images, the severe class imbalance, and the high variability. There are several things we would like to try out regarding future work. First, we could experiment with other segmentation models. This one is pretty much well known. It's a benchmark model. We could try something a bit different. We could include the slices which we discarded because they did not contain any pixels with lesions. For this, we could, for example, include a slice classification step prior to the segmentation. This way, we would not be discarding data, and we could still do the segmentation only in the slices where there are pixels with lesions. Finally, we could try a 3D approach, which is computationally more expensive, but it does in fact come with less variability in the masks. And also, when we turn the data into 2D, we lose some inter-slice information, obviously, but our results seem to show that it's not a big difference in performance. So we went with the low costs in terms of computer performance and easier to implement when you don't have super expensive computers. So thank you. If you have any questions.
We have now 5 minutes for questions. Any questions from the audience? Nope.
I just have one. It's not related with the technical part, but more on the motivation. So what do you think is the motivation for the segmentation? Like, what is the utility of that for the clinician?
I think it's a very high interest when it comes to disease stratification. So not in terms of diagnosis. If you have COVID, it doesn't matter how large the lesion is. It does matter when you're trying to to stratify the disease and make a prognosis. So for patient prognosis, it can be very important. Several studies show relations between the extent of the lesion and, for example, patient mortality, or if it goes to the ICU or intubation rates. So I would say that the interest of this sort of stuff is mostly for patient prognosis and for stratification, mostly because you cannot perform a CT scan on everyone that comes to the hospital, right? You would do an X-ray for that. So in my personal opinion, I would think that we should focus on X-ray for diagnosis and on CT scans for prognosis. When we already know the patient has COVID and is maybe at the ICU and we want to know how bad the damage is.
Okay, so it's more like an intermediate step. So imagine like you have like future work starting from this point.
Yeah.
Something that could be of interest is like starting from these segmentations and trying to predict like how long they will stay in.
Yes, some studies actually already do that.
Room or something.
And usually they combine that with other indicators, for example, clinical data or results from other lab tests. So leukocyte counts and, for example, stuff like that, and blood counts and so on. But usually the most relevant indicator is in fact usually the volume, because then you go from segmentation to calculate the volume of the lesion or lesions. Sometimes there's more than one. And there's usually a strong correlation between that and patient outcome.
Okay, thanks.
Any other questions? No. So yes, thank you very much, and thank you very much for the very good question and the follow-up and the very good answer as well. Indeed, prognostic is very important, and so having a measure of volume of the lesions is for sure something that will be very valued. And there's two questions a bit more technical that I'm a bit worried about just looking at your work, which is the 3D to 2D, and of course you mentioned that you want to go now and do a 3D, but the direction where you do the cutting. So from the 3D to 2D, did you check different directions? Did you change the results?
No, we only use the axial plane. It's the plane where you can see most of the information, and where the plane where every other study was using. I'm not even sure if you can get, well, maybe in the other planes we could also try that out. Something that I found interesting on the literature was, I was quite scared that, oh, am I the only one using a 2D approach? But no, actually most people go for a two-dimensional approach, maybe because the computational power is too large, I'm not sure, or maybe it's just not worth it. I was worried myself, and then when we were looking at related work before presenting the work at a conference, the majority of the studies used 2D approach, cutting with the axial plane.
Okay, great. And regarding the false negatives, which from what I could see could influence quite a lot the volume that you would determine, any explanation for that? Anything that you can think that you could do to kind of alleviate that?
Well, yes, but it comes with a certain cost. So we know that in medicine, usually the false negatives are much more serious than the false positives. You can always tweak the model to have a higher precision and lower recall, or the opposite, so a higher recall and a lower precision. So yes, you could, in an extreme scenario, you could completely eliminate the false negatives, but that would mean an extra amount of false positives. So you kind of have to play with those percentages, and some people actually predefine, okay, what is the maximum number of or percentage of false negatives that I am able to accept, and they kind of condition the models from start using those conditions. So yes, you can do something about it, but it usually comes with a cost, which is lower precision.
Totally, but in this case the false negative is basically saying that you don't see any lesion. And so you basically maybe at some point underestimated the time that the person would stay at a hospital. Would that be what do you think in this case, what would be best?
I think that in the medical context, it would always be more, well, when there's costs involved and so on, it becomes more complex. But if you focus on the health aspect, I think that the false negatives are much more serious than the false positives. So you're telling someone they are not sick and they're actually sick and something bad can happen to them. Of course, it's also bad if you tell someone they are sick and they are not. But yes, those are, the models are definitely not perfect, and I am very interested in seeing what would be the consequences on a downstream application, so for prognosis.
Okay, great. I had another question, but we have no time now, so
maybe
thank you
later.
very much. Maybe later.
Thank you.
Okay, thank you. I think maybe now we're ready for Joana Rocha, or should we go to...
Yes. Hopefully you can hear me now.
Yeah.
Yes, we can hear you. We still cannot see you. Great. Nor the slides. Okay, we can see you.
Okay, if you could please share my slides. And also I'm hearing myself, so perhaps just cut the feedback. Okay, yeah, that's perfect. Good afternoon. My name is Joana Rocha, and I'm a researcher at Inestec. Sofia is one of my colleagues, and this work was also, let's say that we have two great advisors, Professor Aurelio Campilho and Professor Ana Maria Mendonça, who are also contributing to this work. Today, I will be briefly presenting my work on explainable AI for automated thoracic pathology screening. This work is aligned with the main motivation for the TAMI project, which is the significant incidence of thoracic pathologies. But more specifically, today's presentation focuses on thoracic abnormality detection in chest X-ray images. So starting with the motivation for this work, this is a very useful task to prioritize certain exams, especially if we consider two aspects. First, that the chest X-ray is currently among the most common medical imaging exams. And then second, the consequent high workload per radiologist. And I cited here some studies that I found quite interesting because they show objectively that there is often disagreement among clinical experts regarding a certain diagnosis, and also that the diagnosis is influenced by the experience of the radiologist, which obviously makes a lot of sense. So we're looking at abnormality detection as a way to provide a second opinion to the radiologists in order to make this diagnostic process more efficient. So in this work, we focused on the VNDR chest X-ray dataset, which includes a total of 15,000 frontal chest X-ray scans. I won't go into much detail regarding the pre-processing stage of the images. Basically, the main idea was to simply crop and resize the scans into squared images and then normalize the intensities. And the original data set includes a total of 14 pathologies described here on the right. As usual, the no finding label translates the absence of the other pathologies. And you can also see here the original distribution of all the labels, which in our case, we transformed these initial classes into normal and abnormal. So this resulted in around 10,000 normal examples and 4,000 abnormal ones. And it is obvious that there is a class imbalance here. So here is the big picture for the proposed abnormality detection framework. The idea is to build a CAD system that is able to receive a pre-processed chest X-ray scan and output whether that scan is normal or abnormal. So this is basically a binary classification exercise that acts as a triage step preceding a more detailed pathology classification step. But simultaneously, this system should also have a black box explainer that complements the prediction with a visual justification. And this is extremely important to understand why the model made such decision through the implementation of explainable AI. Now, we also have an important step along the way, the region of interest cropping step. that will be explained in more detail in a few slides. But ignoring that step for now, let's focus on the abnormality detection model. So this is a very quick summary of our model optimization routine. We implemented a two-stage fine-tuning of a mobile net, initializing with ImageNet weights. We also performed cross-validation with data augmentation on the training set. And then to address the class imbalance problem, we used class weights in our loss function. Our baseline experiments basically established two scenarios. The first one, including or excluding a dense layer between the global average pooling and output layers. And then the second one, unfreezing a smaller or larger number of pre-trained convolutional layers during fine-tuning. And we concluded that pre-training a larger number of convolutional layers seems to slightly increase the performance in this particular exercise. But in fact, there's no relevant difference between including or excluding the dense layer. And overall, we get an AUC of 97.6%, which is very similar to the state-of-the-art results. Next, we analyzed the results regarding the false negative and false positive counts. We noticed that we have a 10% false negative rate in comparison to a 7% false positive rate. So it was important for us to understand which samples are contributing the most to this higher false negative rate. And we concluded that the algorithm fails the most on images representing cases of atelectasis, calcification, and interstitial lung disease. But at the same time, keep in mind that these classes are among the ones with a fewer representation in the data set. So I guess it would be expected a worse performance in these cases. Next, we moved on to the analysis of the explanations provided for each prediction. These were achieved using the GradCam method. And here we have some true positive and true negative examples. Now, on the first row, you can see that the model made a correct prediction by looking at the anatomical regions of interest, but that is not the case in the second row. And in the second row, the model was right about that prediction, but for the wrong reasons. In these cases, the model looked at the lettering present at the top of the images, or even at other artifacts, such as this watch, to conclude on the normality of the scans. Regarding the model's incorrect predictions, we can confirm the negative influence that these artifacts have on the results. Again, in the second row, we notice how these artifacts and pieces of jewelry are being accounted for when they should in fact be ignored by the model. Of course, that ideally these pieces should be removed by the patient before the exam. Leaving these necklaces and clothing on during the exam is considered to be a bad practice, but obviously we still wanted to address this challenge in order to improve our results. And this is why the region of interest cropping step was added. We used another model to detect our region of interest, the thoracic region, so that we could crop out that area in an attempt to exclude these artifacts from the images and at the same time restrict the model's attention to the thoracic region. And adding this step significantly improved our precision and recall. And you can also see here that we were able to lower the false negative rate, which is extremely important in the medical setting. Taking a look at the new GradCam results, we notice how the cropping was able to successfully exclude most of the artifacts, in this case, the R and the necklace. So the cropping basically acted as positive predictions into true negatives. It was also able to correct the false negative cases by forcing the model to look at the thorax and find abnormalities within that area. So for instance, in the first example, the model was now able to detect that the patient has an enlarged individual outcome. So adding this step as a positive influence for both the false negative and false positive counts. So including the black box explainer component allowed us to understand that algorithms take shortcuts and how important it is to evaluate why the model is predicting a certain outcome, especially in the medical domain. So it would not be acceptable to deploy a model that looks at these artifacts instead of the correct anatomical regions. And in this particular exercise, we managed to remove most of these artifacts while simultaneously improving the model's performance. Of course, that in certain situations, the region of interest cropping step is not able to completely remove the artifacts. We have certain images in which the necklaces are on top of the thorax, and in those cases, our approach is not enough to eliminate them. But most importantly, we should keep in mind that explainable AI is fundamental to make sure that we are building a reliable model that can be safely implemented and that is able to provide these accurate justifications for the corresponding predictions. Thank you very much.
Presentation. Any questions from the audience?
I have one.
Go ahead.
Hi, Joanna. So,
Hi.
yeah, as you mentioned that in your conclusions, it's right that these models typically look to some biases in the data. There is even a Nature paper from this year that highlights that most deep learning algorithms published for the COVID-19 actually looked for biases and not for the relevant features. So what you said makes perfect sense. But one thing is like, so if you want to do that cropping, I assume that maybe I was not paying enough attention, but I assume that you need a ground truth for the bounding box. So you need a bounding box annotation, right?
Exactly. Yeah.
Yeah, and in you may not have it. So, do you have any idea how could you do it, like in a weakly supervised manner without having the bounding box ground truth available?
I think the easiest way to do it, and it wouldn't be as accurate as having a separate model basically trained to detect where the thorax is, would be to simply do a basic center cropping. So basically just removing a frame around the image that you have until you have basically just the thorax portion. The issue with that is that not all thoraxes are centered. Some are shorter, some are taller. So that way won't be as accurate, as efficient as having a separate model to detect the thorax region.
Yeah,
but you could do it.
Yeah, and I did not work with the data set you mentioned, but I did work with Shakespeare and Mimic, and there are some X-rays where so like the entire X-ray does not appear, so it only has like half of it. So the top half, and yeah, in those cases, I assume that this bounding box algorithm may fail as well. Yeah, but thanks for your answer.
Thank you very much.
Any other questions? So, Joanna, in terms of using this in a hospital, from what I could understand from your presentation and also from Wilson's question, the way the cropping, it will help get rid of those pixels that don't really have the information that we need. But if we would have to choose the box manually or in another way, it would not be that helpful. But imagine now that you're able to solve this. In what scenarios in the hospital were you thinking besides the one of reducing work for the radiologist? In other scenarios that you think this could be useful?
But you're referring to chest abnormality detection in specifically?
Chest X-ray automatic detection of abnormalities. This is more for
I think the main
think?
Yeah, I think the main goal is always to provide a second opinion. I don't think that having these algorithms by themselves judging and diagnosing a disease would be interesting, at least for now. We want to help the physicians and improve their process, not substitute them in any way. So this has the ability to provide a second opinion that can make the diagnostic process faster and perhaps help and basically have more patients being diagnosed in a less amount of time. I'm not sure if that was your question.
I would. There's another. Actually, there's the main goal of this type of models is really because the radiologist is not always available in a ER, for instance. So, in fact, one of the main reasons why we want this type of models is because if we don't have the radiologist, if we have, for instance, a primary care physician that is not so used to identifying lesions in a chest X-ray, we want to have some algorithm that would be able to alert us to the need to send the X-ray to the radiologist. So, not really as a second opinion, but more as an alert mechanism, it would be extremely useful as well.
But again, you will always need a validation, a human validation after the alert has been made. So again, when I say second opinion, it means that there has to be an expert validating the output that comes out of the algorithm.
Second opinion would be the radiologist himself. So, but just to keep going, this is a very interesting and very needed algorithm, and hope you the best luck. Thank you very much.
Thank you very much.
So now we have Wilson Silva.
I'm not sure if
Whenever.
this is working or not, but
let's just wait
could
for
you
the
please
slides.
provide me with the slides? Yeah. Yeah. No pressure. Okay, thank you. So my name is Wilson Silva. I'm a PhD student at Philp and a research assistant at INESC-TEC. My scientific supervisor is Professor Jaime Cardoso, and my co-supervisor is Professor Maria João Cardoso from the Champalimaud Foundation. So she's a surgeon. And I will present here part of my PhD work that is related to interpretability or explainable artificial intelligence, and that served as motivation for the CMU Portugal project TAMI, and the work I currently develop is under this project. Okay, so as Joanna said, currently clinicians and radiologists face an excessive workload, which may contribute to an increase in undesired diagnosis mistakes. And one way to prevent this is to introduce decision support systems to help radiologists make decisions. But most of these systems nowadays is based on deep learning or ensemble models, so very complex models that also lack interpretability. And to be able to use them in a clinical context, they need to be interpretable. And one way to achieve that is through case-based explanations. So case-based explanations are one way of explaining model decision, and we think they are really interesting because they feel natural to radiologists because they are used to look to images. So during my PhD, I developed interpretability techniques and explored the impact of case-based explainability in these three different clinical applications. So the first one is the static evaluation of breast cancer treatments, and this was the main motivation for my PhD. But I also applied these techniques to melanoma detection in demoscopy images, and more recently in pleural effusion diagnosis in chest X-ray images. So the first work I did in this line of research was basically instead of considering the image as our input, we first extracted from this image some high-level clinical concepts defined by the clinicians. And then we explored the semantic space close to the decision to find the meaningful and representative explanatory examples. And in the case of the aesthetic evaluation, the feature extraction process was done using this software, BCCT Core, that was developed by my supervisors. So basically, we had a deep learning model with some regularization strategies to make it more interpretable, particularly with monotonic constraints. And as I told you, we used as input some high-level clinical concepts. Some of them had monotonic behavior, some of them don't. So we had two different branches in our network, and we applied this network to these two data sets. So to BCCT dataset, which is related to the aesthetic evaluation of breast cancer treatments, where we considered 23 features, mainly measuring symmetry, color differences, and scars, and the Ph.D. dataset, which is related to melanoma detection, where we had 14 features quantifying the presence of certain colors or abnormal patterns. And this work was done in collaboration with the Champal Foundation and was published in a workshop at MICAI, which is the main conference in medical imaging. So I'm mostly talking about case-based explanations, but our motivation here was to have a diversity of explanations. So not everyone thinks in the same way, and there are people that think more in a verbal way, and others that prefer visual explanations. And as was said in some minutes ago, the end user of the explanation could be a radiologist, which is quite used to images, but it could also be a general clinician. And maybe for a general clinician, like a rule to explain why the diagnosis was made maybe easier than an image, and like for a radiologist, an image is always better because they are very used to it. It's what they do. Another topic that we introduced in this work, and it's quite important, it's the evaluation of the explanation. So most of the times, the explanations are evaluated in a subjective manner. So you show them to clinicians and they just say, okay, I agree, or I don't agree. But one thing that is really important is to have a quantitative way of evaluating the explanations. And in this work, we came up with some proxy functions that we called the 3 C's of interpretability, which is completeness. So an explanation should be applicable to more than one data point. Correctness, so if we consider an explanation as a machine learning model, it should be accurate. And compactness, so an explanation should not be based on all features of the feature set. In a following work, we wanted to increase even more this diversity of the explanations, and we came up with an ensemble model that was constituted by this deep neural network previously presented, and also by a scorecard and a random forest. So a scorecard is a very common model in finance because it's highly interpretable. And the random forest is in itself an ensemble model. And so here we have 2 rule-based explanations given by this scorecard and this random forest, and our case-based explanations given by our deep neural network. And another thing that we introduced here was a way to have a global explanation for this ensemble. And it's described in this equation that is presented here. And it's basically the global explanation. So the explanation of the ensemble is the explanation given through the model that agrees with the ensemble decision, and that leads to the maximum correctness. So what was basically based on those proxy functions that we proposed. Okay, so in those first works, we were focusing on the classification part and then on trying to produce explanations. But during my internship in Switzerland, so in collaboration with Inselspital and Universität Bern, and during some talks with one of the board-certified radiologists there, he really told us that what he was really interested was in a system that when he is facing some dubious diagnostic case, presents him with some really similar examples from some past cases that are already diagnosed, and that could help him make the decision. So we started working on content-based image retrieval systems, and after a search, we conclude that most of the available systems were focusing on the entire image. So they were looking for the most similar image. But that is not exactly what we are looking for. We want the most similar image in terms of disease and disease severity. And the disease is located in a very specific region. So we tried to come up with methods that helped us identify these relevant regions, ideally in a weakly supervised manner. So we can come up with more focused representations and with better image retrieval. And this work was published at MICAI last year. So basically the approach consisted, we called it interpretability guided content-based image retrieval, and it consisted of a two-step training process. So first we have like normal CNN, we use the DanceNet, and given the images, we just trained our algorithm and then generated some saliency maps. And for that, we used the deep Taylor interpretability method. And after having these saliency maps that ideally locate the regions of interest, we then fine-tuned our previous model. And to do the retrieval, we then went to the previous to last layer, so a very semantic space, and just computed the L2 distance between our test case and our well-curated catalog images. And then ranked in terms of similarity, but not like in the original space, but in this semantic space. And for the experiments, we used the well-known Shakespeare dataset, and we created 5 different sets with catalogs of 10 images each. And so we had like 5 test images, and for each test image, we had a catalog of 10 images. Then we asked our board-certified radiologists to rank those images in terms of similarity when taking into account the disease and disease severity. And then we evaluated the performance of the different methods with this NDCG metric that was also shown in a previous presentation in retrieval in terms of text, but here we also use it. And for the retrieval, we use this SSIM, so the Structural Similarity Index, and as like a normal CNN approach, which is basically our step 1, and then our approach. And as you can see, it resembles much more closely the radiologist than the previous ones. And here I just show some examples, and you can see what I basically am talking about. Okay, so this was Elena's presentation. So if we are dealing with explanatory, with case-based explanations, that could be a problem. That is the privacy.
Time is over, so if you
okay.
go to
Yeah, I will wrap up. So basically, I will just say that case-based explanations could be a problem because there is an identity that could be exposed. So it's really important to anonymize these explanations. And these are 3 properties that we think are relevant. And yeah, this was one thing that we tested, but there are still some downsides. So the realism of the images is still lacking. And Elena also described some other problems with that. So as you can see, this work is, these are the TAMI goals, so the CMU research project. What I talked here, it's quite aligned with the first 2, so quantitative methods to assess explanations and to provide better explanations by providing complementary explanations and adapting the explanations to the consumer. Okay, so just to finish, what we are planning to do. So currently, I'm just finishing a paper, a journal paper to be submitted, where I just test the methods that I published at MICAI with a new data set. And I'm also investigating other approaches to find these more appropriate feature representations. And one of the approaches is attention. I will keep working in these multimodal explanations and also trying to explain multimodal data. So when we have image and clinical report, and keep working on these privacy-preserving models to anonymize case-based explanations and ideally integrate causality into this. Okay, thanks and sorry for
Thank you, it's fine. We'll just ask
delay.
a few last questions. So, first, very good work.
Thank you.
Congratulations. Any questions from?
I have a question. What sort of explanations are you able to get from the random forest? Because decision trees are inherently explainable, but the random forests are not always inherently explainable, depending how you combine the trees. So is it a variable importance score, or what type of explanation are you able to get from them?
So basically, the explanation for the random forest is extracted using that equation that I shown.
Okay.
So like the decision tree is an interpretable model, as you said. The random forest is an ensemble, so it's not that interpretable, but our final decision for the random forest is the explanation from the decision tree that agrees with the random forest, and that leads to the explanation with the highest correctness.
I thought the equation was for combining the three models.
It's for both.
Oh,
so
okay.
The equation is to provide an explanation for an ensemble model,
Yeah. Okay.
and this ensemble model had an ensemble model inside.
It's an ensemble of ensembles.
Exactly.
Okay.
Yeah.
Perfect.
So
Thanks.
the explanation for the random forest was extracted.
Also with the equation.
Yeah, exactly.
Perfect. Thank you.
Any other questions? So I have one question. So the explanations that you found, that you had for the images, were they related to features from the images? Did you explicitly do that relationship between features and explanations, or it was just, text on one side, image on the other, and then somehow?
Regarding the first work.
Yeah.
So yeah, so I think I forgot to mention that. So I had in the first work I had the deep neural network. I was able to extract like a rule-based explanation using sensitivity analysis, and for the case-based I looked to this semantic space, and then what I did, or what we did, was to look for the nearest neighbor of the same class, and to look for the nearest neighbor of the opposite class in this semantic space. And then also did a sensitivity analysis to check which features were contributing them to be similar or to be different.
Okay.
So in the case of the factual explanation, we tried to understand which features were the most relevant for them to be of the same class, and for the counterfactual, which features were the most relevant for them to be of different classes.
Okay. And what about the completeness of the explanation space? How did you assess if it was complete or not?
So it depended if it was a rule-based explanation or a case-based explanation. But for instance, if it was a case-based explanation, so this work was like 3 years ago.
I'm sorry.
but if I remember correctly, so for the case-based explanations, I looked to the nearest neighbor from the same class. Yeah, so I looked to the nearest neighbor from the same class, and having these, I was able to compute like a diameter, and then I looked to all data points that fell inside, and the percentage of those numbers over the entire data set.
If it was all inside, it was complete. Okay, great. Thank you so much.
It was the percentage of data points that fall inside the explanation.
Yeah, great. We have to stop, unfortunately, but thank you so much again for a great presentation. So now we have Fernanda Fama with a very different topic, very interesting as well, and very applicable in healthcare. Go ahead.
Good afternoon. I'm Fernanda Fama. I'm a Ph.D. student at the University of Coimbra. I'm working in the Dual project. This project is a partnership between the Institute of Systems and Robotics, CMU, and other internships. So my thesis is a smart IoT gateway on the edge for patient condition classification and monitoring in digital healthcare. So we have seen an increase in IoT devices in different contexts in our daily use, such as industrial, public, private servers, urban, and domestic environment. Digital health is one of these contexts that's associated with IoT, are changing our perception of how healthcare is delivered. So during COVID-19 pandemic has increased the number of remote medical appointments. However, despite the importance of this area, only 7% of IoT devices are used in health area. So we studied and saw a clear need to continue studies and remote frameworks for real-time monitoring, allowing analysis in the domiciliary environment to improve the population's well-being. So the CMU Portugal project was objective to design and develop an intelligent IoT-based interoperable healthcare system to patient management through several wireless biomonitoring sensors and secure acquiring and transmission of data for analysis, process, and visualization. So we have bio stickers with biomonitoring attached in the patient's skin. These stickers have sensors embedded, so they send the data through wireless communication using Bluetooth Low Energy to a smart box embedded in the patient bed. Because of that, we have a smart bed. This device collects this information and send for smart gateway. This smart gateway acquiring all the data sent by the bio stickers that is sent for a smart bed and sent for a hospital information system. In this case, is GLIN, Global Care. But the system provides one interface for healthcare professionals looking and monitoring and to analyze this data. So the initial plan was to store and processing the data in the cloud to discover patterns and anomalies in long-term acquisition. However, this approach has some limitation in terms of delayed system response, increase the communication cost, and the data vulnerability in terms of privacy and security. Some example of vital sign that we can measure is temperature, heart rate, respiration, ECG, and others. So the proposal Ph.D. plan, my idea is to bring artificial intelligence techniques beyond the cloud to the edge of the network for patient condition classification and monitors. This way we can classify some disease in the edge and provide a system to critical alerts. So the edge compute allows us to reallocate computer resources to close to the data source. And this approach has some benefits in terms of transmission, energy, bandwidth, can improve the privacy and security, and also, as I mentioned, bring the computation to the edge of the network. So the artificial intelligence and the big data is a clear trend in handling the data generated by the IoT in healthcare. And we saw some relevant techniques work on that. The example of the PROT-NN is an algorithm to classification, the bone size, another algorithm to prediction, and we also have the distributed training based on gradient descent. All these techniques used on this algorithm, AI algorithm, such as KNN, linear regression, and other, and also deep learning, but also applied to and adapt to limited resource device. So our plan is an overview of the proposed solution. In the first layer, we have the patients, the bed, and the smart beds, and that send this data towards Smart Gatorade, and with the edge device, compose the edge computing layer. The Smart Gatorade is more to local database and to respond critical function for the system, and the edge device provide more processing, data processing in terms of pre-processing, data fusion, data filtering, data classification, and training, and also develop a system to critical alert healthcare professional or some familiar, some parents to some problem with the patient. But we also have the cloud service to continue to monitor in a long term the data collected, so we can predict it and solve the patient in a long term based on this data. And we also have the user interface, the hospital system information system, and the integration with all this one and the other ones, and the data processing and so on. So the next steps is do a literature survey on the use of artificial intelligence classification for healthcare, do a comparative study and benchmarking, to develop and adjust multimodal sensor fusion classification methods for patient monitoring, and do an experimental design to propose performance indicators with relevant evaluation metrics. And during my time in CMU, I intend to do the implementation and the integration of the methods within the WAL architecture. And in the end, do the validation of the system in real-world pilots. So thank you very much.
Thank you very much. Any questions from the audience? Not this time.
Not this time.
So this is extremely interesting and extremely important. We more and more need home care, so we need to take people from the hospitals and have them stay at home for many reasons. And this is extremely important to be able to provide safe care to these patients while they don't have in many cases, the healthcare professionals or even the people taking care may not have the training required in critical situations. But on the other hand, we have 5G now, right? So one of the problems that you mentioned about the delay that you might see, would you think that with 5G, if it becomes ubiquitous, this is something that will still be needed to have the processing at the edge instead of the cloud?
Yes, because the 5G is related with this kind of edge computing, but the cloud is necessary because the edge can provide a large number of storage or computation, so they help. If you put a portion of this process, allow it to classify and to monitor, but we need the cloud to have a long term or to storage this data and help. And so the 5G is a merge between the edge compute and the cloud compute. So one dependent of another.
Yeah, great. So and so the goal at this point is just to get a critical alert of something that is not it's not going well. So
yes, also, but in terms of the internet drop, the connectivity drop, you have a system to alert, to provide some guidance, some process to this data until the system come back, return.
Okay.
So in terms of transmission, we have this part, but also we are seeing the next step to improve all the system in the edge.
Okay.
So also we can predict some disease, but not cancer, something like that, more quickly, or based on multimodal sensor fusion when we have some problem with temperature, and also other vital signs, some in terms of ECG and other. We can have this small part of the processing in the edge.
So basically generating an alert and some type of classification of severity of what the action would be from the hospital or the institution that is monitoring the patient. That's,
yes.
Okay.
Yes.
And so I know it's early on in your work, but have you assessed costs in any way? How would this compare in terms of costs of having kind of a higher power processing unit at the bed of the patient versus just sending the raw signal to the cloud?
Yes, we in this just moment we have run a pilot in the hospital in Coimbra with my team. So we it's very low the cost of the bell, because we put in a print, a specific print to this, and the CMU is helping in provide this equipment and all the system that we need. So we don't have we don't calculate in a large scale, but in a small scale it is easier. It's not that course. In the example of 5G, we need a network, a dense network, to improve the actual 4G to provide this. So this is more lower the cost than in this case.
Okay, great. Thank you so much. Any other questions from the audience? If not, then I'm going to thank the speakers. There were 4 very interesting presentations, and good luck to you all. And thank you. Good afternoon.
Thank you.
Thank you.